we're doing theory that as a foundation of all the techniques that we have used and the things that we have applied, but now we are moving towards more precise statements, and that these are what explains the definitions that we've had. So actually 3 definitions in a row, and there's a certain challenge to them. Linear combination, first of all, of vectors. It is a fancy word, but it is an abbreviation of something that we have been using for a while, and just as a matter of convenience, because the abbreviation of what? We have exactly two operations in linear algebra for vectors: addition and scale multiplication. If you try to pull them together, you end up with linear combinations. That's all. So there is nothing more to it. Okay, so it's just more convenient, more compact. Instead of saying addition and scale multiplication, just say linear combinations. Okay, so the second one, and the span. Okay, so it is the set of all linear combinations of these vectors, and they might produce something. They produce a set. Okay, remember, well, actually there's one more definition that that started everything, and that was a subspace. Where's my definition of subspace? Linear combinations, illustrated, and subspace. So it's actually 4 definitions. And the point of the definition of a subspace is to on the surface, as you can see, it preserves the linear combinations of 2 or more vectors within it, which means that addition can be carried out within the subspace, and scale multiplication. Okay, so in other words, such a subset is a special kind. So it is like a microcosm of all linear algebra, because you can whatever that is, you can carry out all linear algebra within that set and be done with it, not worrying about it. Everything what we have learned can be carried out within that set. And we would have seen many examples when subsets are very, very non-trivial, and in fact they emerge very naturally from solving systems of linear equations. So in fact, so that would be next topic to discuss. In addition, just as soon as we finish with this, just trying to list all the subspaces of R2 we have, the spaces of R as they are lines through the origin. Okay, now if we want to try to if you want to try to move on to the next dimension, okay, so if we are talking about R3 now, all lines and planes through 0 are the subspaces, non-trivial subspaces of R3. Once again, in addition to the 2 trivial ones, 0 and the whole space. So all lines and planes. Okay, every line, so there it could have a slope, could have 2 slopes, incline, but they are subspaces, which means that they are entirely algebraically self-contained. Okay, so you can imagine that nothing else exists, and you can do algebra within them. Okay, so but the challenge is, as we keep moving up dimensions, what would be the next theorem in R4? So what are the subspaces of R4?
Lines, planes, and 3D spaces.
Right, 3D spaces, so lines, planes, and 3D spaces. Which is really the last part is questionable, because at least we think we understand what lines and planes are, but what is a 3D space is not, if not, a subspace to begin with. Okay, as you go in high dimensions, you start thinking about Rn. Then what are the subspaces? If not, at best you can say what I have already said a few times: copies of Rm with m less than or equal to n. Okay, so the best you can tell, kind of circular language. Then we explain the subspaces in terms of subspaces, and but what is subspace? We want to demonstrate eventually that there's just Euclidean a copy of a space Rm. Okay, so then there's just language that kind of works out, and it is very visual as far as the lower dimensional spaces are concerned. It fails in high dimensions, and we are simply, it's not a problem. We really simply have to go back to the, not back, but rather forward towards the language of subspaces. So these are the subspaces, and you don't have to classify them in a particular way, a visual way like this. You have to classify them based on their dimension. Okay, so this number is what we need to figure out the meaning of. Okay, so as you can see, so once again, if we just step back to dimension 3, lines are one-dimensional, planes are two-dimensional. If we go to dimension 4, these are one-dimensional, two-dimensional, three-dimensional. Okay, so then it is the word dimension becomes what allows us to classify the subspaces. And so all we need to do is to figure out the meaning. What does it mean for a subspace to have a particular dimension? What is the meaning of dimension? It is quite a profound question to begin with, and we're going to address it. You see, all it is more than what we just have seen. We already seen multidimensional spaces, but they were specifically Euclidean. Okay, so they were built to begin with as Euclidean spaces, as strings. N-dimensional Euclidean space is a set of strings of n numbers. Okay, so it comes with a dimension sort of known ahead of time. What if you have something going on that you don't know what it is to begin with? It might be the solution set of a system of linear equations, and then what is its dimension? Remember that another way to describe this is to speak of the number of degrees of freedom. That's what dimension is. Okay, and then we want to figure out how you can determine it by looking at that subspace. So all of them are possible under the circumstances, and we just need to figure out what it is. Fortunately, it's not. We're already on the way in that direction, and the answer is, and the answer is, I suppose we should just try to ask ourselves what is the meaning of dimension in Rn. So meaning of dimension is what we want to ask, and based on the examples that we have already seen, we do not want to it's not an option anymore to look at what it is, but rather look at where it comes from. So let's go back to this example that I'll keep coming back to, because it is what linear algebra ultimately all about. It is about solving systems of linear equations. So let's do that example again, repeating this for a while. I think 0, 1, 0. What? Undo. Okay, 1, 0, 0, 0. So I have a reduced row echelon form. Like this. Hold on a second. How do I do it? So this is the reduced row echelon form, and homogeneous. Okay, so if I do this, and my augmented matrix has no last column, the vertical line, and there is nothing there. It means that there are zeros. So this is homogeneous. So if this is vector matrix A, so what we're talking about is simply this. This is my system. So I'm left with a matrix that actually is the original matrix of the coefficients of my system. Okay, so suppose this is what it is, and okay, so we found the reduced row echelon form, or rather, it is the reduced row echelon form. Okay, now we should be able to write the answer now explicitly. So this is just a matrix, and we convert this into a vector form, in order to represent explicitly the solution set. So what's the vector form of this? Or that, it's the same thing. The vector form of a system of linear equations. What is it? It is, in fact, it is a linear combination. A linear combination of the columns of the matrix. So remember, we're looking for x1, x1, x2, x3, x4, right? The unknowns. Okay, so they serve as the coefficients of these vectors that together form a linear combination. In fact, it just applies equally well to non-reduced Rorschach form. And it's supposed to be equal to 0. Okay, so this is the vector form of our system. Okay, and as you can see, this is a linear combination. A linear combination of the column vectors of A. So decomposing our matrix of coefficients into columns is a crucial step. So it will also reappear a few times. Okay, so where is and then what we observe here is that every solution is a linear combination. Every solution is here. So the combination of number x1, x2, x3, x4 is a linear is supposed to be so that when substituted into this formula, it would give us 0 on the right-hand side. Okay, so indeed, every solution, combination of x1, x2, x3, and 4, it is a vector, but it's secondary right now. It is a linear is given by a linear combination of the column vectors. Okay. No, I didn't put it right. Every solution comes as the coefficients, of a linear combination of the column vectors. Okay, so that it would produce the right-hand side as we want. It happens to be a homogeneous system and producing zeros. Okay, so the point being is that we want to recognize the we want to recognize the how should I put it? The vector subspace structure in our solution set. Okay, so let me just put it in the form of a theorem. The solution set of a system of linear equations over Rn, homogeneous system, is a subspace. So once again, the solution set is a subspace. We have seen many examples in the past, remember? So we would, I keep coming back to those examples. So let me do it one more time. Not this one. Here it is. Okay. So you're solving a system, okay, and well, actually that's not the example. This is the one. This is probably a better example when the your solution is expressed explicitly in terms of what? Two vectors. And as you can see, it is indeed made of nothing but all linear combinations of those two vectors. Okay, so if you are in the reduced Roche form, that's what you convert your system into, and your vector equation becomes this, and the set of all linear combinations. So that we know that's why subspaces is represented as spans. But really, what I'm after right now is to go beyond that, and even though we have seen those systems of linear equations producing subspaces several times, we don't really have to. We now can just demonstrate this fairly easily by using certain properties of linear matrices. Okay, so let me quickly show what I have in mind. So suppose x1 and x2 are solutions. Okay, so what does it mean? Ax1 is equal to 0 and Ax2 is equal to 0. Okay? Okay, so there is nothing else. And then let's form a linear combination. So let x be equal to, say, ax1 plus bx2. A linear combination of these two solutions. Okay? Now, what I'm supposed to demonstrate, remember what the definition of a subspace. The definition of a subspace is that it contains all of its linear combinations. So, okay, so I took two elements in the solution set, form a linear combination of those, and then I want to demonstrate that this is also a solution. Well, it's uncomplicated, so we just check. The solution has been suggested, so we don't have to look for it. We just have to plug it into the equation and see if it works out. So I do AX is equal to, it is after all a matrix multiplication, AX1 plus BX2. What do we do with this? Distribute based on, can you quote a property that justifies that? What?
Distributive property?
Yeah, it is. It is actually. What did we call it? Actually, I guess it is more like the sum rule followed by the constant multiple rule. Or a linearity rule, where those two operations are combined together into one. So, but yeah, you distribute it. Why? Because that's what we know about matrix multiplication is that it behaves this way. So it preserves addition. So it is equal to first ax1 plus a bx2, okay? So that's like the sum rule of matrix multiplication. And then I'm using the constant multiple rule, so to pull these out, ax1 plus b ax2. And now what? All of the ax1 and ax2 are zeros, right? So it's a times 0 plus b times 0, and the whole thing is equal to 0. So yes, x is a solution. Okay, so that's a crucial step in our analysis. So the solution sets are subspaces in a sense. We're gonna let's make sure that we are on the same page of what this means. Subspaces are appear as solution sets of system of homogeneous linear equations. Once again, homogeneous is simply 0 on the right. Okay, so otherwise there's no big difference to worry about. And the examples are what we have seen already: those lines through the origin, planes through the origin, are subspaces on one hand. They are also all possible solutions to homogeneous systems of linear equations. Okay, so and I also want to emphasize that for later, that in a sense it's the same thing. So solution set is a subspace, but vice versa, it's also every subspace is a solution set to some system of linear equations. It's the same thing in a sense. Okay, so now how do we figure out though the dimension? What is the meaning of the dimension of a subspace which might appear in a very implicit way? I mean, we may have not even solved the equation entirely. We just know that there is an equation. How do we explain the meaning of the subspace that it has produced? So its solution set is a subspace, and we want to understand what the dimension of that subspace is. Before we go back to systems of linear equations, let's just look at subspaces and understand what is the meaning of its dimension is. Fortunately, we don't have to really work that hard because the idea comes from, so once again, what's the dimension? What is the meaning of dimension of a subspace? So the answer comes from the structure of Rn. Okay, so Rn, we certainly know what Rn is. It is strings of, all strings of numbers, x1, xn, x1 real, xn real. Okay, so that's what this is. The set of all strings of n real numbers. Okay, and so we know algebra, how to do algebra with them. And we know by design, naturally, what is the dimension of Rn. It is the way we have called it. We call Rn the n-dimensional Euclidean space. So, and certainly whatever we want to come up with the idea of what dimension is, it's supposed to match the idea of the concept of dimension of the standard Euclidean space such as this. So you cannot certainly, it's not going to look the same way, so that's the challenge. But if we look closer at the structure of this space, we can understand where dimension n comes from. And let's just take a lower dimension. R2 is just a pairs of x1, x2. Okay, x1, x2 are real numbers. Okay. Okay, so but really, what if we think in terms of vectors? Let me actually let me fix this. I do prefer now for this particular example to look at these as vectors. Okay, so we are studying vectors, we're not studying points. Oh. Okay, so what does it make? What makes it two-dimensional? This is what the standard basis vectors are E1 is equal to 1, 0, E2 is equal to 0, 1. Okay, so what is so special about these vectors? The fact that we know from a while ago that every vector in R2 can be expressed as a linear combination of these. Remember that? Discussion from earlier this week, right? So if I have a vector AB, then it is simply equal to A E1 plus B E2. Okay, so that's really what the idea is. We're trying to understand the dimension of these spaces without referring to what? To that specific way we have constructed them. So whatever this is really not something that we want to refer to. We want to understand the linear algebra of these through some indirect way in order to take that idea and apply it to subspaces later. Okay, so that's I'm trying to do that. And indeed, this one could be used later in order to understand what a two-dimensional space would look like. Okay, so once again, look at it. So every vector in R2 can be expressed as linear combination of E1, E2. Okay, so let's tweak this a little, and then can we have the same property with other vectors, with another pair of vectors? Still in the plane. What do you think? So the properties is this fact over here. So can we replace E1 with 2 with, say, V1, V2? Well, let me capitalize it. Such that the still every vector in R2 can be expressed as linear combination of V1, V2. That's right. As long as they're not parallel, it would do the trick. So let's just do specific example. We did it, I think, in the past. So how about I pick V1 is equal, how about, I still pick the 1 the same way, 1, 0, and I pick V2 to be 1, 1. Okay, so as long as, once again, the answer is yes, so the answer is yes, as long as, not just there is 1, but in fact there are a bunch of them, as long as they are not multiples of each other. So I am suggesting then this example of 1 is 1, 0, the same as the original one, and 1, 1. So instead of these, E1, E2, I'm dealing with these now, V1, V2. Okay, so it is kind of, I hope it is intuitively clear that why this is true to begin with. We talked about spans sufficiently, so we're talking about linear combinations of these two vectors, and if you remember the discussion from Wednesday, the span of this thing is either one or the other will give you the whole thing. So if you take the span, it gives you the plane. If you take the span, once again, it will give you the whole plane. Okay, so but if you want to do it specific, then prove it rather than just jump to conclusions. You would do what? You would say x. You have a vector AB. You have a vector AB, and you want to represent that vector AB as a linear combination of these two. So it will be x 1, 0 plus y 1, 1 equal to AB. Okay, you need to find x and y. So as you can see, everything, all of these new concepts there, on one hand, they are really come from solving of system of linear equations, but then you can, to actually make sense of them, you still have to go back and interpret them as systems of linear, solving system of linear equations. So you're supposed to be able to solve this system of linear equations for whatever A and B are. So is this solvable for any AB? Okay, so that's slightly a new idea here. No matter what A and B would pick, we're talking about representing every vector in the space, every vector AB as a linear combination of those two. So we're looking not at one single linear system, but rather at all of them altogether. As long as A and B are there to be, we form a vector from them. So all of these is the solvable for every B, and the answer is indeed it is right here, the same thing. As long as they're not multiples of each other, it is true. We can demonstrate fairly easily if we just prove that statement that we made over here. So it will be 1, 0, 1, 1 AB. Okay, doesn't matter what AB is. Remember that when we're dealing with elementary row operations, once again the last column is simply there for a ride. Okay, we're doing something with the other two. So what I do is just I subtract. So I have to have the reduced Rorschach form. I put here R1 minus R2. So I'm getting 1, 0, A minus B, B, 0, 1. Okay, and then so what we see is it has been solved. It is solved now. That doesn't really matter exactly what those numbers are. Well, even though we already have them. Okay, so So in fact solved, so let's make it specific just as well. So vector AB then is equal to what? It is equal to, well, tell me what it is.
Are you asking for like an example number?
We are saying here that every vector can be represented as linear combination of v1, v2, okay, which means that any vector meaning AB can be represented in such a combination. So since this system has been solved, we should be able to just write up what that linear combination is. Remember what the system represents. We were looking for x and y, and we have found x and y. X is a minus b, y is b. So we can write a linear combination here. So what is it?
A minus b times
Yeah,
1 over
v1,
yeah,
b times v2. Okay, so we have found it. Okay, so more generally, once again, if you don't know ahead of time whether or not such a representation is possible, you sort it out by you solve that problem. So you're given two vectors and you ask yourself, are these two vectors can serve the same role as E1, E2? And how do you answer the question? You solve the system of linear equations, and it turns out that it is indeed, it works out every time as long as these two vectors are not multiples of each other. What does it mean, multiples of each other? Look at these, by the way. So if we try to take this sentence over here and not multiples of each other, so they aren't multiples of each other. What does it mean in terms of our matrix? Our matrix, after all, is made of these two. They aren't multiples of each other, but this is where they are. We put them as columns of our augmented matrix. So in other words, what we're saying here is we're saying that the matrix would have to have two rows that are not multiples of each other. So not multiples of each other once again. So which means that based on that idea, I could come up with examples of vectors v1, v2 that work out easily in that manner because I already know the answer. So as long as these two columns are not multiples of each other, the solution will work out, right? As we just demonstrated. So for example, I could have 1, 2, 3, 5. So these could be my two vectors, and once again, they can serve as the same role as E1 and 2. So at this time, well, before we finally make all the definitions that the time comes to make, what about? So we picked 2, but why did we pick 2? We could try to pick the number other than 2. So the property I am concerned about is still the same. So this is my property that I care about. We have found a way to resolve that issue. Let me rewrite it. We found a way to resolve the issue when there are two vectors, but still. So suppose, not suppose, but rather. So v1, vm are vectors in Rn. Okay, so, well, maybe I'm jumping too far. Let's take v1, v2 are vectors in R2. Okay. And once again, they satisfy that property. It's possible. What about v1 if there's only 1, and what if there are 3? Okay. Vector in R2, and these are also vectors in R2. Okay, so once again, this one is yes, provided. The answer is provided. Well, the question is, can every vector in R2 be represented by as a linear combination of these? Okay, and the answer is, and now I have three versions of that question for three situations. One vector, two vectors, three vectors. Okay, so we answered the second question, provided they are not multiples of each other, right? Okay, so let's answer question 1 and 2 and 3. So what about the first one? No. Can you explain why?
Because even if you multiply by multiple, it'll always be the same.
Yeah, so indeed, so if, say, x isn't a multiple of v1, then we're done. Then we cannot represent it. Okay, so one vector will not do the job. Okay, so remember, we're trying to understand why this dimension of R2 is 2. Okay, so 2 little is not enough. Less than 1 is not enough. R2 is fine as long as there isn't some requirement. What about 3? Can every vector in R2 be represented as a linear combination of 3 vectors? The answer is yes, okay. But then how does it work with if you compare it to part 2?
It has the same restrictions.
Let's see. So the answer for part 2 was yes, whenever v1 and v2 are multiples of each other. So would that answer work for part 3?
Two of them could be.
2, right. So that's the trouble. So you could still have 2 of them multiples of each other, but as long as the third is not, it will still work out. Okay. So the conclusion is what is the conclusion? So the answer is yes. It's just the answer would be but why? Meaning that if you need 2, you don't really need 3. Okay, so if you can do it with 2, why would you do 3? So we're looking for the minimal possible combination of vectors that would solve this problem. Okay, it's called the basis. Okay, so given a subspace, vectors v1, vm form a basis. Its basis, if to begin with, so that property is still a requirement. Every vector, well, let's say v, no, w, v is fine. Every vector in v can be represented as a linear combination of v1, vm. Okay, so that we gotta have it to begin with, and then but we don't want to have too many. We don't want any redundancy. But not if we remove any vector from this collection. So in other words, if you have 3 vectors and you can, and the answer is yes. Whenever the answer is yes, you can represent all vectors in R2 as a linear combination of these three. It means that we can drop one out and it will still be good. Okay, so then it is a basis. It satisfies the property we're looking for at the top, and it also a minimal possible, so there is no redundancy. Okay, and then now the key step is then in that case, M is the dimension of V. So in other words, how many elements you need in a basis. Okay, so once again, that discussion not like a long time ago, I don't think probably in the previous notebook, the systems of linear equations expressed as linear combination of vectors, and we had, it is a four-dimensional system, and we have like 5 possibilities, and exactly fits this situation. They were varying from dimension 0, 1, 2, 3, and 4. So these are the 4 possibilities of a solution of a system of linear equations with the, even though those solutions are not Euclidean spaces themselves, they are subspaces. Subspaces of, in that case, was R4. Okay, so I guess I'm out of time. So I'll just try to sort out what's going to happen.